So the basic outline, we've done a number of these, and each time we kind of overlap a little bit to make sure that there are people who have maybe not participated in earlier ones or want a little bit of a refresher. So there's a quick review: why fusion, a little bit of the history, the core of fusion science, essentially, which is to a large extent uh, can be characterized as the Lawson criterion or the equivalent so-called trip uh, criterion, and Q, which is the overall energy gain, and that really helps define the core of all this. And then we'll talk a little bit about the key aspects building into taking a tokamak-based fusion reactor and making it into a power plant. Then there'll be some recent fusion news and an update on Commonwealth Fusion that has been put together by Commonwealth Fusion on a regular basis now. And then we'll talk about the first wall and the material challenges and issues. And I have some references and URLs. So, why fusion and history review, the core of fusion science, binding energy of the nucleus, possible fusion reactions, the DT reaction in particular, and deuterium and lithium as fuel. And then we'll talk a little bit about confinement and the Lawson criterion. Then we'll talk about the tokamak-based fusion reactor, the plasma core, where all this good stuff happens, the first wall that keeps the plasma core isolated from the rest of the world, the breathing blanket, which is essential to convert the lithium into the tritium, magnets, which we talked about earlier version of this update, auxiliary heating, and then there's sort of everything else. So why fusion? Well, this is new from a year ago. This gentleman from University of Washington gave a lecture at a DOE-sponsored summer workshop on plasmas and fusion. And last year, it was a very hot topic that AI was going to make the demand for power centers, for data centers, get much bigger problem than it currently was. And there was a quote here that I thought was interesting. And an average a ChatGPT query needs nearly 10 times as much electricity to process a Google search. And so, of course, these kind of estimates are just throwing a dart at the wall, but the relevant point is that it's going to go up substantially. And I showed this one before, again, from this gentleman, Bhuvana Srinivasan. How does fusion fuel compare to other energy fuels? You can see how a small amount of fuel is needed for fusion. It's the back of a pickup truck. Fission, you need a little bit more, smaller than a big truck, but a good sized truck. And pretty soon you get into oil and coal, and you have enormous numbers of involved in these things. And that's just because energy is so much more concentrated in the nucleus than it is in the electrons that are responsible for all chemical changes. Another way of looking at the same thing. Comparing actually fusion and fission, they're not all that dissimilar. A kilogram of fuel for fusion, it gives you about 10 to the 14th joules, and essentially about half as much kilogram of a uranium for a fission reactor. The units involved here, the 676 and 176, are the use of one U.S. citizen in 1 year, according to the Department of Energy. And showed this one once before. The value of the availability of the fuel. There's an inexhaustible supply essentially in the oceans. It essentially makes energy available without worrying about about fuel, because everybody can have access to the fuel because there's so little cost to it. It's clean. It's capable of fitting right in with any kind of a electric power grid and the kind of demand issues that come along with meeting the demand. And fusion does this. Some of the other renewable type things don't, because you can't schedule them. It's safe. There's essentially no possibility of meltdown like scenarios. You can have internal damage can happen, but it doesn't cause damage outside the plant. So, brief history. Arthur Eddington is sort of considered to be the sort of godfather of fusion, when he speculated that the energy that ran the stars might be available on Earth. And work that had been done already about masses showed that when you combine together four hydrogen masses, the mass of helium was a little bit smaller. And the difference, of course, is from E equals mc squared is an enormous number. Cecilia Payne, who later became Cecilia Payne Gaposchkin, and did her work at Harvard, actually recommended by Eddington to go to Harvard because she couldn't get a PhD in England as a woman. She published her doctoral thesis showing that hydrogen is a primary constituent of the stars and the most abundant element in the universe. George Gamow in 1928 introduced the idea of quantum tunneling to go through the potential barrier. And Mark Oliphant in 1933 demonstrated that the process worked when it was done with a accelerator in the Cavendish laboratory. Hans Bethe later was instrumental in understanding the actual nature of how the stuff Eddington talked about really worked. So if we start with binding energy, nucleus, of course, full of protons, depending on whatever the element is. And in order to keep it from flying apart, there has to be some force that acts with protons and neutrons in an attractive fashion to overcome the electrostatic potential energy that's trying to blow the nucleus apart. And so if you take the nucleons by themselves, you have to add this binding energy and essentially to construct this nucleus. And then the delta E, delta mc squared shows you the amount of energy that's available. This was the first observation of transmutation effects observed with heavy hydrogen, paper that was written by Mark Oliphant, originally from Australia. And he bombarded things with protons, and then eventually with heavy protons, or as they called them, diplons at the time, which are now known as deuterons. Proceedings Royal Society, 1933. This is actual data from his paper. These are observations of what he called 14 centimeter protons. This is the amount of material that in the case of this experiment, air, that these protons would penetrate from a DD bombarding with accelerated deuterium, a substance with deuterium in it that was to target. And he also saw tritons coming out, because when you do the DD fusion, there are two branches. One branch produces helium, and the other branch produces a triton as well. This is the summary, and this is what they said, that a group of protons of 13 minus 3 centimeter range is emitted in very large numbers. A shorter group of singly charged particles is also observed, and shown the two groups contain equal numbers of particles. Those are the two branches. And the shorter one, obviously, was the triton. And this is the interesting here, is that at 100,000 volts, only 1 in a million reactions occurred. And this is just a little aside here. I asked the Google OpenAI function on Google search to explain this. And this is what it came up with. The AI summary said he was an Australian physicist known for his work in nuclear physics. Well, yeah, okay. He played a role in the development of first nuclear fusion reactions in the lab. Yeah, okay. His experiments involved the use of deuterium and tritium isotopes. This is kind of deceptive, because he observed tritium, but he did not use tritium in his experiments. He contributed to the understanding of the condition necessary for fusion to occur, and his work laid the groundwork for future research in nuclear energy and fusion technology. And those are okay. He was later involved in the Manhattan Project, but had nothing to do with the hydrogen bomb. It was just involved with the fission. But GPT, you're going to see later, is not always so good. So here's the binding energy curve for the different mass numbers, and this is the binding energy per nucleon in MeV. You can see the peak occurs right around here, iron and nickel, pretty much. Very tightly bound, reasonably tightly bound over here, and a very low mass number. And from this point on, decreasing. So everything from here, you get energy out by fission. And on this side, up to iron, you can get energy out by fusion. It's kind of a highlight of the part of the curve that's interesting, and added in the beryllium because it wasn't there, even though I had lithium 6 and 7. So the problem is basically that when you try to make a bigger nucleus, you have to now overcome the Coulomb potential, which tries to keep the new particle from being added to the nucleus. So here you have an approaching proton. It runs into this potential barrier, and essentially, if it wasn't for some sort of extraneous effects, fusion would essentially never happen because this potential barrier is high enough. You need extraordinarily high energy incoming proton to overcome it. But we have a breakthrough that is due to quantum mechanics and also the fact that there is a tail to the distribution function of energies. So this is what you compare. Coulomb scattering has a cross section or effective size in a sense, and so do the fusion reactions. And you can see that the Coulomb cross section is always higher than the other cross sections, which means you've got to keep bouncing these things around to make sure they have enough bounces for this fusion to occur. That's what the confinement is all about. The two aces, though, are Maxwell-Boltzmann distribution, way out in the tail, and the quantum tunneling. And George Gamow came up with this calculation and showed the effect of different temperatures, the distribution of, see the low temperature and then the much higher temperatures. So the effective cross-section of a fusion reaction for most of these reactions just doesn't look very good. People like to talk about D helium-3. It has a very low cross-section. This is a log scale, of course, compared to DT. And the DD produced, as was observed by Oliphant, two branches. One produces helium-3 and a neutron, and the other one produces a triton and a proton. I won't go through all the details here, but the temperatures involved are very high, even with all these good sort of helpers. The sun operates at quite a low temperature, 15 million degrees, which for a kilo electron volt, 10,000 degrees Kelvin. So 15 million degrees is just 1.5 keV. Right. See it right in here. DT, this blue color over here, is the best from the cross-section standpoint overall, and it requires the least ion temperature. The P boron 11, which is talked about by some people because it doesn't produce any neutrons, is the very hard one to do. The one that everybody wants to do because of the helium-3 on the moon, D helium-3, is this orange one. And it does pretty well in terms of overall cross-section, but you have to get to much higher temperatures. So these are considered the four viable reactions. And these two, as pointed out, have no neutrons, but they're hard to do. This one, if you do this, it's a little harder than DT. It has one branch that produces no neutrons, but it produces tritium. And if you produce tritium, you end up with this reaction too. So the question is then, break even is considered that the amount of energy going in plus the losses is equivalent to the output of the fusion reaction. Ignition means that the alpha particles heating in the DT reaction provides enough energy to keep the plasma at a high enough temperature to fuse without any further energy input from the outside world. And the Lawson criteria are just, and the triple product are just ways of saying the same thing. And fusion gain is just characterizing the total energy. So this is Lawson's original paper. It was classified when it was first published. And Lawson basically evaluated a very simple situation where you had fusion power being balanced by radiation from the electrons in the presence of the protons, known as Bremsstrahlung, stopping power, stopping radiation. Lawson envisioned a couple of scenarios. The first scenario, which shows the Bremsstrahlung power, the fusion power due to the alphas. And you can see the representation. This representation was not his. This is a paper by Sam Wurtzel, who I met when I was down in Washington a couple of weeks ago. He's written a sort of an updated version of Lawson's work. So Q fuel is defined as fusion energy over heating energy absorbed by the fuel. And as these are slides from Sam Wurtzel's talk. And as Lawson used R instead of Q, but whatever. This is how you can convert Q fuel into the standard Lawson criteria, the density and the confinement time. And Wurtzel followed his original model and extended it to other sources of energy loss. But this is what Lawson observed overall. Even with the most optimistic possible assumptions, it's evident that the conditions for the operation of a useful thermonuclear reactor are very severe. That's in circa 1955. And it's only now that we're really getting to the point where we believe we have the basic understanding in hand to, we can say, yeah, it's coming. Q fuel greater than 2 requires that you have high temperature and also high product of density and confinement time. And there's some more analysis. So today, people talk about not so much the original Lawson criteria, but both Q scientific, so-called break-even, and the so-called triple product, which is basically the original Lawson product multiplied times the temperature. Yeah. This is, again, Sam Wurtzel and his colleague, Howe, wrote a paper in 2022. It's now available. Anybody can download it. And included impurities, profile effects, and other things. And when you look at this column over here, the break even occurs right at 21, 10 to the 21. Without the temperature, it would be down here. And you'll notice there are a whole bunch of different kinds of fusion schemes that have been plotted on here. There's hundreds of tokamaks. They are the dominant ones, but there's dozens of other things as well, from reverse field pinches and stellarators and And of course, also this stuff up here is all inertial confinement fusion, NIF stuff. The Q equals 1 break even, scientific break even, is this green one over here. But to do engineering type of break even where you have enough energy to run the plant and things like that, you need to be upwards of 10. And you can see that both ITER and Spark are aiming to be in that range. Prior to those machines operating, because they still aren't operating, you have D3D down here, you have JT60 that's in Japan, and you have JET, which got very close. So this is again an AI overview, loss and criteria. But the AI didn't want to stop there. It wanted to go beyond. So when I asked it for Q equals 1, it came up with this analogy, which is wrong. Imagine heating a pot of water to boiling. The Lawson criteria is like saying you need to heat the water to a certain temperature for a certain amount of time to get a certain amount of steam. Q equals 1 is like saying you're putting in the same amount of energy to heat the water as you're getting out as steam. For a useful power plant, you would need to put in less energy than you're getting out as steam. So Q would need to be greater than 1. Obviously, that doesn't happen. That violates one of the fundamental rules of thermodynamics. The only reason that this works as a definition is because there's a reaction going on that's not just converting water to steam, but essentially is making water out of hydrogen and oxygen, if you think about it from a chemical reaction as opposed to nuclear reaction. But the chat box didn't figure that out. So this is a plot from a relatively recent course offered at MIT on the MIT Open courseware. Anybody can download that course and take it if they want to. And these numbers over here are years. So this is the old Soviet T3. This is the thing that basically convinced everybody that they wanted to do tokamaks. Princeton converted the Stellarator that is now at the National Museum in Washington at the Smithsonian into the symmetric tokamak, or ST, 1971. I first heard about that in 1971. And Alcator A came along later that same year, basically. I was involved with it as a student laborer at first because there was a law that occurred in the magnet structure, and when they tried to cool it, turn the magnet on, it had a breakdown of electrical insulation, and it had to be cleaned and reassembled. And so that's what I did first with tokamaks. This chart just is kind of a gratuity for my own pleasure. All those numbered things on there are tokamaks I've had my hands on working with. Started with Alcator. It was no longer available, so we built number 2, which is called Versator. And we can see it's a lot less capable. After I finished rebuilding Versator after the end of my undergraduate period, I did some work with Alcator in the summer there, and then later I came back to Alcator when I came home for Christmas vacation one year from Texas. This is a machine that I built and worked with my advisor from MIT, who had moved on uh, to UCLA. And then these are the two tokamaks I used and worked with in Texas. This was pre-text. This my PhD work was on this one, and this is the bigger tokamak text, which is sold to the Chinese and is now called J-text, still in operation. So, review of this stuff here for DT fusion. That 10 to the 21 number comes up for the triple product. This is Q equals 1 is scientific break even. Q equals 5 is what is called the burning plasma, where alpha heating is providing self-heating. Q infinity is ignition. You don't need any external heating at all. And engineering break even is in there somewhere where it takes into account that you could make it worthwhile, but maybe it doesn't pay to do it because of economics. Commercial break even is once you get necessary where you can compare the cost of energy produced by a fusion reactor to the other sources. So Professor Srinivasan asked this question: have any fusion concepts that achieve scientific break even? And essentially, there are two that, by definition, scientific break even over for this laser project is a little bit of an artificial number because there's a vast amount of energy needed to make the small amount of energy that actually goes into the hall room or the little capsule. And if you allow for all that other energy be free, then you can come up with a Q of 2.36. Very recently, they produced a year ago or so, they produced 5 megajoules of energy. The Joint European Torus in 1997 operated at Q of 0.67. You saw it on the chart there. And it had, in 2024, it produced 69 megajoules of energy. But it was, in both cases, just essentially thermal energy without any conversion electricity. But an interesting little number he put in here, that the average U.S. home uses about 100 megajoules per day. So if you look at this number over here, you go, well, that's a big number, but 69 megajoules divided by 100, that's a city-like potential operation, small city. So this is a summary of all the tokamaks that he thought were interesting, worth telling about. This one in Korea, this has gone back and forth between Korea, a tokamak in France, and a tokamak in China for the length of the duration of the discharge. That's not really a particularly relevant parameter, but it's good for competition. That's jet right there inside of it, and this is ITER. This is another way of looking at that same information that we saw before, except now it's plotted on, instead of on temperature basis, plotted on the calendar basis of years. So you can see here's the progress that followed directly from the T3 machine. It just shot up this curve sort of rolled over a little bit, and get this machine at Princeton TFTR and jet get very, very close to that break even condition. This was the Stellarator that was the original Model C, which became the ST. Stellarators went up very fast for a while, then they leveled off, and they still haven't reached the level where tokamaks are. So if we go into what constitutes a tokamak quickly, you have a central solenoid that drives the current that helps to confine the plasma. The plasma actually sees a magnetic field that's both a toroidal magnetic field coming from these toroidal field coils, and then a so-called poloidal magnetic field, which is going around this way, and that's due to the current in the plasma. There are also some coils that are used for shaping and positioning and equilibrium and things like that. So these are illustrations that came from a talk by a staff member at the D3 tokamak, which is operated as a national user facility by the General Atomic Company in San Diego. This is an example of one of their discharges. So you can see when people talk about flat tops and the length of things, that's the plasma current. This is the magnetic field being set up, and as soon as the plasma current gets up to fairly high level, you can see the temperature rises and it gets up to a reasonable number, sufficient for significant fusion. But with the shutdown of jet and the other machines being smaller than jet, D3 is the largest now operating tokamak. And this is an example of the original cross section of these things was circular, and they had what was called a limiter, either a little piece of material that's stuck in from the side or sometimes a complete ring with a hole in it. And that has been sort of superseded by this sort of concept of a magnetic field that has a branching point in the air. That is on the other side of this is pressure is actually higher, but temperature is much lower. And this is the so-called diverter region. And as I pointed out, the coils can be used to shape the plasma as to the relative height versus width. It says you can watch this, but you have to go to this website, and we don't have that. That's the D3 machine. There are different ways you can essentially set up the plasma column, and they result in different ways of confinement and different magnitudes of confinement. L mode and H mode are commonly just used to describe low energy confinement and high energy confinement. Can be different by a factor of 2 or more. The different regimes give rise to different performance features of various kinds, some of which are good. You get more energy out and stuff, but some of them are likely to lead to instabilities of various kinds. And one of them is the so-called Elm phenomenon, which is a mode that is due to the shaping of the pressure. It's called an edge localized mode, or ELM. And ELMs deliver a lot of heat to the plasma facing components, which is not a good thing. There's a bigger problem in addition to these sort of steady state problems that has a big impact on the materials, and that is the so-called disruptive instability. The tokamak operates in a mode, an overall mode where the current is limited by geometry and magnetic field, externally imposed magnetic field, uh, to keep so-called magnetohydrodynamic instabilities from developing. And if they do develop, they can do what's called disruption, which basically interrupts the current and crashes the magnetic field, dumping the plasma into some component inside the machine, ideally that can handle the energy dump. But if it doesn't have that feature built into it, then damage can be done potentially to the inside of the machine. People have looked at different ways to try to prevent these disruptive instabilities. So one of the things that came out very early on was that if you just had pure hydrogen, everything would be fine. But the walls sitting there are being hit by all sorts of things, even with an absence of neutrons and from fusion reaction. Just the hot plasma is bombarding the walls. You go, well, I thought the magnetic field kept the charged particles from hitting things. Well, it does basically, but the problem is that you can have a process called charge exchange where a neutral gas atom can wander in from the outside and hit a ion and transfer the charge, so that now you have instead of this wandering, slow moving neutral, you now have a fast moving neutral, which has no confinement because the magnetic field has no impact on it, comes straight out and bashes the wall and can knock loose more stuff. So this was observed basically early on, and it's still an issue that's being looked at. How do you pick the right material for the wall? So the so-called PFC, plasma facing components, some of them are obvious good things. You get less radiation from these low Z materials, but they typically erode from the wall faster. And therefore, you can get a higher so-called Z effective, which is the effective charge. If you go to a high Z material, you can do very well with the structural aspects and erosion and things. But some of these materials will retain certain amounts of things and essentially lead to high Z impurity accumulation. And that could make it impossible to make it energy wise above Q equals 1 or low number above 1, but far below what's needed to make it engineering successful. So what do you need when you look at a power plant? Well, we have what's called generally the plasma core, which is the plasma itself, any number of things inside the vacuum vessel. That's what this little line is over here, vacuum vessel. Then you will have the breeding blanket because you need to make the tritium, and that's in here. And surrounding that whole thing is the magnets. So this is a toroidal field magnet, and these are the magnets that produce the steering and shaping and things like that, and they're called toroidal field coils. And in the center, this green thing is the primary of the transformer, effectively. It drives the current in the plasma. You need pumps. You need a steam generator or something equivalent to get the heat out. And then you need what you'd have in an ordinary thermal power plant, whether it's nuclear, whether it's coal, or whether it's oil, natural gas, or even a thermal solar plant. And all of them would have structure look the same out here. Turbine, cooling towers, cooling water, condenser. So if you cut this part off, even you could really cut it off right here. Now you're talking about the unit that could be delivered on potentially on a barge or perhaps a rail cars, not have to be assembled out of small parts, but a plant can be assembled out of pretty large parts. See, it's a human scale. So the plasma core, first wall, and the breeding blanket, plus things that are on the inside of the first wall. The magnets, the auxiliary heating, either neutral beams, very common in the earlier days, less so now, or radio frequency. And then you have everything else: pumps, power supplies, cooling, fueling, control, diagnostics, and the power plant itself that takes the heat from the reactor and makes it into electricity and puts it on the grid. So Commonwealth fusion, which came out of MIT back in the 2015 timeframe, the idea began circulating around, and students taking a course put together as the course collective project a design for a power reactor based on these new high temperature superconductors. And the professors liked it, the students liked it, they formed a company. That company was incorporated in 2018 and set upon building this Spark, which is a sort of a double acronym. ARC is a compact reactor, and Spark is essentially a prototype for that, or test reactor. And these are the parameters of the so-called Spark reference pulse. If everything works, this thing may be doing this kind of stuff in the next 2 or 3 years. The machine itself should be finished this year, maybe slides a little bit into 2026, but it's essentially finished this year and begins operating next year, probably without any attempt to make fusion, and then a couple of years of that kind of work, and then they're ready to put the tritium in and try it. So at this point, we want to look at the first video. How does heat get into and out of the plasma? This talk is presented by the essentially head engineer for Commonwealth fusion.
You can think of it like convection, just like the conduction or convection. The plasma, the heat just like kind of leaks out the edge. That is eventually concentrated down to the bottom due to the magnetic geometry, so I won't talk too much about that. But the power will come out that way. In a power plant, you want to capture all that energy. So people like often think about like neutrons. Oh, those neutrons are bad. They just activate stuff. No. We want neutrons because like that's where all the energy comes from. Like that is the revenue. That's the electricity that we are putting on the grid. We need the neutrons. But you can't just like let them go anywhere. You have to collect that energy somewhere intentional so that you can use it to make electricity. So here's again my cartoon. Here's a toroidal field coil. Here's a central solenoid. Here are some colloidal field coils. Here's the fusion happening in the plasma. You surround it with some kind of material to absorb those neutrons. There's a bunch of ways you can do this. We have chosen a molten salt called FLIBE. It is a fluorine, lithium, beryllium salt. Typically, you want something that has lithium in it. So I haven't talked too much about like where do you get the tritium from, but I'll do briefly on that. Deuterium naturally exists. You can filter out of seawater. Roughly 1 in every 6,000 hydrogen atoms on Earth is deuterium. Tritium does not occur naturally, so you have to make it. But if you hit lithium with a neutron, it will create tritium. So basically, our plan to produce the tritium is produce it yourself inside the tokamak and use that to fuel the tokamak. This molten salt also then gets hot because you've just put a bunch of heat into it. You then pull that out. You get the hot salt out. You heat exchange that with water. You make steam. You spin a turbine. And you connect that to the grid. So I'll say a little bit ironically, we're doing all this like crazy technology development to build this magnetic chamber in 100 million degrees and And it's like the best way to make electricity is still to boil things and put it through a turbine. Turns out works really well. And that is the strategy. Future looking, there are other ways to do this. Totally fair. We will look at that in the future. Largely our strategy to date has been like, this part is really hard. So like do the hard part and like don't unnecessarily make other parts harder. So like choose a super well commercially proven technology of like I can like call a steam turbine manufacturer and be like, I'd like part number 3 from your catalog. And like we ourselves will focus on this like totally new challenging part, which is the fusion part. So all to say, that looks very, very standard. There are other things you can use for this molten salt blanket, or for a blanket in general. Typically, it has to have lithium. You can use liquid lithium, like metallic lithium, lead lithium. You can use lithium ceramics that then you cool with something else, like helium. Bunch of options, all somewhat challenging in different ways. We think this molten salt solution is the best overall solution, although it is certainly going to be a challenge. This is not just like some theory cartoons we're drawing. We do have like very concrete plans to build this facility. It's actually not too far from here. It's a couple hours. We will build the ARC power plant. It's actually already on Google Maps in Chesterfield County, Virginia. So this is a Google Maps picture. We announced that site roughly 6 months ago. Right now it's still a field, but we do not too far in the future, we'll start actually doing development on that site. We have very strong partners, both state and locally. We wanted a site that wanted us, so we like talked to the community. They're like, fusion, yeah, sounds cool. Like, let's do it here. We also have like very strong partnership with the local utility, Dominion, who will like basically, put that electricity onto the grid. And we're very late stage discussions with offtake agreement partners, like the person who's going to buy the electricity. Also, Virginia needs a lot of electricity, so they're very happy to have more power plants come there. And we're moving fairly far along in the engineering design of this facility. You might look at this and be like, well, that looks kind of like that other thing you're building, which is exactly the point. So this is a slightly larger version of Spark facility layout, but again, tokamak here, a whole building dedicated to maintenance, which would be challenging. Some of the measurements and tritium in the front. A lot of the standard industrial equipment in the back here. On the left, this is this molten salt piece to take the heat out. This is a turbine hall with a very boring but very effective steam water turbine in there. Switchyard in the back. And these are dry cooling towers, so not evaporative towers. A little bit less efficient, but means you don't need nearly as much water intake to the plant. More plasma happening. And so that's a bit of that's like an overview. And so like as a company, our goal is build on known science. Advancing science is very important. That is not our mission as a company. Our mission is to make electricity. Build on known science, combine it with new technology, bring it together in Spark, learn exactly what we need to get to a power plant, and go build that power plant. So high level view, that's what the power plant is. A little bit on like the road ahead, like where are the challenges, where are the opportunities. Fusion is hard. I agree with that. No one's saying this is easy, but we are saying it's worth trying. Part of the job, honestly, which this isn't very sciencey, but is like Spark needs to continue to happen. Like this is a large, first of a kind, complex engineering project. And like every day you need to do a thing. It's like I mentioned earlier, like we make one pancake a day. If we did not make one pancake today, like we did not do our job today. So like we need every day, you just need to continue to execute this project. Again, not the most scientifically exciting thing, but just like super important for like building big stuff. As I said before, we need to do some science and technology. So learn some stuff on Spark. On Arc, we'll continue to do some R&D in parallel. So produce and test materials that will withstand the thermal and radiation conditions in Arc. Develop and test at scale FLIBE molten salt components. So people have done a lot of FLIBE stuff at kind of lab scale or maybe a little bit bigger. We need to make like industrial sized pumps, industrial sized pipes that have industrial sized heat exchangers attached to them. So there's a lot of like industrial scale up that needs to happen on this FLIBE technology. As well as some tritium science and technology understanding for arc scale. So like a very large throughput of this tritium material separating out of the FLIBE, that kind of thing. In parallel to the R&D and building Spark, we're continuing to design Arc. This is another engineering product. We're still in the fairly early stages of the design. As you can see, like most of the stuff we have now is like not super detailed. It's similar to where Spark was in maybe 2019, 2020, early on in the stage of that machine. So we call it the pre-conceptual design phase, and things evolve rapidly. So the team comes together, design, does a bunch of analysis for like, these things need to change, come together, a new design for Arc, make these changes. So it's a very rapid, quickly changing thing. And you might also say, like, wait a second, how can you design this next one when you haven't even finished building the first one? Great question. A lot of the plant you can design without knowing the exact detail of what this shape of the diverter leg looks like to get your heat out. You can design like the pump for the molten salt system. You can design some of the tritium stuff. So the goal in this early design is to like be as flexible as possible in the areas where we know we have the largest uncertainty, so we can include late design input from Spark. And this is less than the technology, but maybe also an important piece of this. I mentioned earlier that the goal is not to build one of these, one awesome. We need to build thousands to have a real impact. And it's like part of this is like the ecosystem. So like we need to build an ecosystem in the world that is ready to do fusion. Like when the technology is ready, which is not quite there yet, but it's close. When the technology is ready, we need a world that is ready to accept and rapidly deploy fusion. So this means regulation. Very, fitting being here in DC. The UK and the US have both decided to regulate fusion like a particle accelerator. The US, this was ruled by the NRC in 2023 and then passed into law by Congress in 2024. So this is regulated like a particle accelerator, very, very separate from fission. It's a risk-appropriate framework, different risks, different regulation. We also are, hoping that other countries will follow a similar framework where you don't have to like completely design a different power plant in every country because there's different regulation. In addition to that, we need to develop a supply chain. So we are already actively doing this. We have an active supply chain team at the company. Just this superconducting material over the last 5 years has scaled up a massive amount. Like when we said we were originally going to do this, 5-ish years ago, people were like, you can get all this tokamak stuff, fine. You'll never buy enough superconductor to do that. And it's like, it was hard. You had to like work very closely with suppliers around the world to help them scale up. But like they saw us, they're like, there's a customer. There's a real customer who's going to buy this stuff. Like we will scale up. So part of that supply chain development. And I think one of the common things we get, especially within the fusion industry, is that like, each one of these machines is so hard. How will you ever build that many of them? It will not be easy, but to build all of the superconductor, all of the HTS you need for 1,000 arc plants in a year, you'd need like 5 first solar thin film factories. It's a lot of factories. It's not that many factories. You need to make pancakes, those layers of the magnet, in one Tesla Model 3 factory. And you need to make the cases, the steel of the magnet, in one Hyundai Heavy Industries shipyard. So like all of this is to say that like the technology is hard. And on top of that, scaling it up will be hard. But when you go talk to like heavy industry, like people who build stuff and build it at scale, they're like, yeah, you could scale that up. Like, if you can figure out this like fusion thing and like you can actually make this work, we can build a lot of it. And so I think, for myself personally as well, coming from an academic background, coming from the physics background and going into industry, like this part seemed like impossible. There's no way we can do that. And you would talk to people who do this and they're like, yeah, we'll figure that out. It will be challenging. We can figure it out. But again, this comes back to one power plant's cool, 10,000 power plants changes the world. And it comes back broadly to our pathway to a fusion future. So I will say that's a bit about me. It's a bit about fusion. So fusion, basic process, powers the universe. Hopefully, potentially a huge game changer in the energy industry. We are working on a type of machine called tokamak. People built a lot of these. We are combining that with a new magnet technology based on high temperature superconductors. We're now building a spark tokamak just outside of Boston. And we are getting ready for the ARC fusion power plant in the Richmond, Virginia area in the early 2030s. So thank you very much, and I'm more than happy to take questions.
Yeah,
Thank
hold
you.
it for a second. It was questions.
Yeah, Steve, Ted, right now, how long can the current equipment sustain a reaction before it's damaged? Not experimentally to see if it runs, but before it's damaged.
Okay, so damage right now is a sort of a hard to specify kind of a criteria, because if you talk about the machine just running normal discharges, the machine they're building now is designed to operate for 13,000 discharges over the next 10 years. And that basically means, it will degrade slowly. It's not going to be damaged violently. It could be damaged violently by these so-called disruptive instabilities and some related phenomena that can melt internal components and things if you don't handle them properly. And one of the things they're trying to learn is how to mitigate those kind of situations.
But right now, how
Yeah.
long can the machine sustain its reaction?
Well, really just as long as you want to keep the power going into the thing. I mean, that's
Okay.
It's a power limited thing.
Okay, I got it. Thank you.
Hey everyone, my name's Alex Creeley. I'm the Director of Tokamak Operations here at Commonwealth. Today we are at the Spark site. And I'm very excited. Made a lot of progress in the last year, still making a lot more progress. Ready to get this machine operating and on in. We'll go this way.
There are almost 1,000 people working there right now.
Welcome everyone. This is the operations to measure what's going on with the sticks. But basically, in order to measure what's going on inside of a plasma, which is 100 million degrees, you need a little bit more than a thermometer. And so we'll have a bunch of different instrumentation here to measure the temperature of what's going on inside of Spark, the density, how much power we're making, all these kinds of things. We do that for two reasons. One is that we just need to run the plant, how fast you're going. So same reason here, we want to be able to control the facility, control what's going on, run it properly. So we'll have measurements for that. In addition to that, though, we want to learn stuff. So Spark is not yet a full power plant, but it demonstrates the fusion technology. It demonstrates that all this works. So we'll make a bunch of additional measurements on Spark so that we can learn things, so we can improve the design of the ARC fusion power plant, so we can improve its operation, and so we can get to the point where we're ready to build this thing and put fusion watts on the grid. So if you want to follow me, we'll go to the next building. Okay, so before we go in to see the tokamak hall, we'll make a brief pause here and just talk about the tokamak itself a little bit. So if you've seen some of these videos before, you'll probably have heard this, but if not, a brief introduction to what a tokamak is. It's a fusion machine, donut-shaped, mainly made out of magnets. We have a little demonstration here. And these are the big toroidal field coils, TF coils. They're big D-shaped. They go around the pink piece here, which is the fusion plasma. That's the fuel, deuterium and tritium, that we use to do fusion. There's these copper things in the center we call the central solenoid. They look copper, really they're also superconducting. And there's these other magnets around here that we call the poloidal field coils that we use to shape and move around the plasma. So all of these magnets, CFS manufactures ourselves, and very soon these will be coming across the street and going into the tokamak hall, which is where we will go next. So if you want to follow me in this way. So we are now in the tokamak hall, which is where the actual Spark tokamak will be built and operated. So as you can see, it's much busier than it was a couple months ago. We have now started the process of assembling the tokamak itself. So the big steel piece there in the middle is the base of the cryostat. That is the bottom of Spark, so everything else will end up getting built on top of that. It has a couple of really important jobs. It keeps the whole machine cold so that the magnets operate, but at the same time, it has to have feed-throughs, which are like basically holes in the bottom to let the coolant in, to have power for the magnets, a bunch of instrumentation. So there's a lot of complexity in like getting all that stuff through properly while keeping the machine cold. So we've started assembly, which is awesome. And very soon we'll start putting some of the magnets together as well. So these two orange half circles are assembly tooling, so like temporary stands where we're gonna start putting the magnets together, start putting the vacuum vessel halves into the magnets, and eventually those two will come together in the middle over the top of the cryostat base, and that's where Spark will be in its final position. We'll finish putting the machine together and get ready to start operating this thing. So with that, we'll head out of the tokamak hall and into the next building. So follow me this way. So we are now in the radio frequency microwaves at the food. The oil and the water absorbs those microwaves and warms up. And we do basically the same thing, but rather than with microwaves, we use radio waves. It's almost FM radio. So FM radio is like, roughly 90 megahertz to 108 megahertz. This is 120, so it's not that far off. But rather than launching the waves out to send out music, we launch them in to heat up the fusion plasma. And so those waves we make back here, there's a bunch of those metal cylinders. Those are basically a way of generating radio waves. We make them there. We pipe them through these pipes that you can see at the top. You can think of that like a giant coax cable that you'd normally plug into the back of your internet box. But rather than sending internet, it sends high power radio. And then those come and into the tokamak hall, plug into the side of the tokamak, and launch those waves to heat up the plasma. So with that, we'll head to the next building this way. So we are now in the power building. So in order to operate superconducting magnets, you need to run electricity through them. And this is where we have all the adapters that make them operate. So on your computer, you have that little box in between the outlet and your computer. That's the thing that adapts the power. Same thing this, a little bit bigger. Utility yards outside, that's where we store all of our nitrogen and helium to run the facility. And the really exciting part is we'll get to see the cryogenics here. So we are now in the utility building where we have a lot of the large industrial systems which will keep Spark operating. Most importantly, a lot of the systems in this building take out heat from the machine. We really do that in two ways. One, at really cold temperatures. So to run the superconducting magnets, they need to be really cold. In this context, really cold means like minus 400 Fahrenheit or 15 Kelvin, which is where we operate most of the magnets. What's awesome though is that we're actually starting to operate stuff. So we've got cooling water systems operating. We're starting to operate some of our helium compressors. We're going from just like building stuff to commissioning and operating, which is a really exciting phase of the project and a really exciting step on our path to operating Spark. So with that, follow me to the next building and we'll talk a little bit about next steps. So as CFS gets into the later stages of finishing this plant, commissioning it, starting to operate, and assembling the Spark tokamak, we're also thinking about what's next. We've just announced the site of our first ARC fusion power plant. It'll be in Chesterfield County, Virginia. We have the site picked out. We're really excited about building a power plant there. And we're already doing some of the early engineering design. We're taking all the lessons we've learned from designing this facility, building it, and incorporating that into the ARC design. So we still have a ways to go. We're earlier in the project. We're really excited about getting fusion on the grid and getting that power plant up and running. So thank you so much for coming to visit today. As you can see, we're building stuff, we're operating stuff, and hopefully when you come back next time, we'll be even closer to demonstrating net fusion energy on Spark and closer to, thanks for coming.
Hi everyone and welcome back to the Fusion Industry Association. My name is Dr. Sid Cowley, and I work at the intersection of fusion and AI at FIA affiliate member DigiLab. Today is Wednesday, the 25th of June, on the News Roundup. Stories today include 1. Major funding milestone for world first prototype fusion plant. 2. Europe's fastest growing nuclear fusion company raises $148 million in record funding round. 3. Nuclear fusion plasma code cracked by US researchers, elusive voids breakthrough. And of course, I'll have some bonuses at the end for you. 1. Major funding milestone for world first prototype fusion plant. Now, I'm so lucky today to get to present to you a few really big stories that have broken over the past few weeks. For our first story, we have some massive funding news from here in the UK. The government just announced an extra £2.5 billion of funding over the next 5 years going to fusion energy. Now, this is a huge relief for all of us in the UK who have been watching closely as the UK spending review has been ongoing. And the government has been deciding which programs to support and which programs to cut. So it's great that the UK has decided to double down on clean energy technologies and this fusion funding particularly, which represents the largest single contribution from the UK government ever to fusion. So it's clear that over the next 5 years, the UK fusion industry and research ecosystems are going to continue to thrive. Though we don't know exactly where that funding is going to go, of course, a large portion of it is going to contribute to the Spherical Tokamak for Energy Production, or STEP, the UK's pilot fusion plant slated to produce net electricity by the 2040s and expected to create 10,000 jobs ranging from construction to operations. 2. Europe's fastest growing nuclear fusion company raises $148 million in record funding round. Our second story comes from CNBC and covers one of the most exciting fusion industry funding announcements in some time. 2 landmark funding announcements in a week. I know, it's exciting. So the announcement is that FIA member Proxima Fusion raised 130 million euros in their recent Series A financing round. The round was co-led by investors Cherry Ventures and Balderton Capital and represents the largest private fusion investment round in Europe to date. Now, as a reminder, Proxima Fusion is a German developer spun out of the Max Planck Institute for Plasma Physics. They aim to deploy fusion energy through the stellarator concept, a magnetic fusion machine with a twisted set of magnetic coils. Proxima may be familiar to a lot of listeners since they have been in the news a lot recently, not the least through the publication of the first detailed concept design of a private fusion stellarator earlier this year. And this progress, both in terms of funding and research, is happening at an incredible pace, with co-founder Francesco Ciortino saying, "The single thing maybe that is worth highlighting is the speed at which this is happening." After all, less than 1 year from its pre-seed spin-out, Proxima raised 20 million in their seed round. And now, barely a year later, they've raised an additional 130 million euros in the Series A. With this trajectory, I, for one, am going to be so excited to see where Proxima will go next. And I'm optimistic that they'll be a real headline success story for the industry. 3. Nuclear fusion's plasma code cracked by US researchers' elusive voids breakthrough. Our third story today comes from Interesting Engineering and covers some exciting new research on something called void propagation in magnetic fusion. The research comes from the University of California, San Diego, and was published recently in Physical Review Letters. But what is this ominous sounding void propagation? And why is it so important for fusion? Well, one of the most important but least well understood phenomena in a fusion plasma is turbulence, where small wobbles in the fusion plasma can spread and mix particles around machines such as tokamaks. And this turbulence impacts core performance and involves blobs of high-density plasma moving outwards and voids of low-density plasma moving inwards. Now, typically, a lot of historical attention has focused on the blobs to understand how turbulence evolves and spreads plasma around. But the team at UCSD have shown that actually the movement of voids of low-density plasma inwards into the core can have a really strong impact on turbulence. Now, this may explain a long-running issue in fusion, where in previous experiments there have been strong mismatches between the spread of plasma that we predict and the spread that we actually see. Now, improving this mismatch could significantly improve our ability to predict what happens inside the fusion power plants of the future. And this is important if we want to know what's going to happen before we turn them on. Right, well, that's all for our main stories, but of course we have some bonuses as well. For our first bonus story today, we have fusion featured in a gaming magazine, GameSpot. Specifically, GameSpot covers the Ulsan National Institute of Science and Technology, or UNIST, in South Korea, and some work they did on algorithms to calculate collisions between fast particles in a fusion machine and surrounding wall material. They compared different algorithms and found that one used in bullets for video games actually worked 15 times faster for this fusion application than conventional methods. So this is really one of those cool cases where fusion research learns from some of the most unexpected places. For our final bonus today, we have the announcement of a new Strategic Innovation Center for Plasma Research in New Jersey called the HAX Plasma Forge. The announcement of the center also comes with $49 million of new funding from the partners of the project, the New Jersey Economic Development Authority and the venture capital firm SOSVE. The center will leverage existing expertise in the area with, of course, the Princeton Plasma Physics Laboratory based there, and feature approximately 10,000 square feet of new and exciting lab and co-working space, all focusing on plasma physics. Right, well, that's all for Fusion News this week, and thank you so much for the continued support on our channel. As always, if any of the stories interested you in particular, their links will be in the description. Thanks for watching. I'll see you next time.
And let's see what people have to say. We can have a short discussion before we wrap.
Okay, so has Commonwealth Fusion or anyone else figured out really the economics of the business? In other words, that not only can they make electricity, but that it can be made at a cost that the market might bear?
Well, there are some preliminary, let's call them guesstimates. It's a long ways away from being able to quote an electricity price that is, But if you think about it, that if you look at a fission plant, about 1/3 of the cost of the fission plant is the reactor. The other 7/10 of it is turbines and generators and switch yards and all those kind of things. So if you just take away the nuclear reactor and replace it with a fusion reactor, it'll be cheaper certainly than that 1/3, that goes for the really massive chunk of concrete. That's the primary biological shield of the fission reactor. But is it going to be cheaper by an enormous amount? Well, probably not at first. In any event, it may get cheaper over time as people learn things about the business. Yeah, so I think the old too cheap to meter of fission electricity never really came about, but we settled in on fission electricity working out reasonably well, and I suspect that fusion will, unless something really strange happens that requires a rethinking or something, it should be in that same kind of price range. And the key is that it's controllable, schedulable. You can call it up when you need it, and that makes all the difference in the world to the electric utility operators. Well, I think on the scaling of things, the spark machine will not produce any electricity, nor will it breed its own tritium. It's purely a development tool to getting to the arc machine. But the spark machine will generate heat, and when it operates, it will be producing hundreds of megawatts of heat that will be vented into the atmosphere in Devons, through a cooling tower. Uh, the ARC machine is targeted at producing in the hundreds of megawatts of electricity. So it has to produce several hundred megawatts in event of heat in order to produce 150, 200 megawatts of electricity. Well, Spark is under construction. The first magnets will be appearing by the end of the summer. They just have to take them and haul them on a big forklift from the magnet factory right on the other side of the parking lot, and they'll start installing them. And by the end of this coming calendar year, the end of 2026, there should be plasmas being produced in the Spark machine, not fusion plasmas, but regular hydrogen plasmas. They probably switch to a deuterium plasma that will produce some fusion power because of the DT combination of reactions that will occur in the following year. And by 2028 or so, they should be operating in that so-called what do they call it? Prime design parameter space with opportunity to do excursions around it and things like that. At that point, they should be well underway in the final design of the ARC machine down in Virginia. So, and I think you'll see power that will be, on the grid in 10 years.
Question about Commonwealth, or more generally, there obviously superconducting magnets are very important to their overall endeavor. What's the global resource situation with regard to the types of magnets and the composition of the magnets that they're using?
Okay, so the magnets are made with what's called REBCO, which is the rare earth barium copper oxide type of high temperature superconductor material. The amount of that material involved is trivial, but the tape that is used to wind the magnets has to be produced in a very precise layering process. There are multiple layers of materials involved. The high temperature superconducting material itself, some buffering material, then there's some silver, there's some copper, and then there's a whole lot of Hastelloy, which is like a fancy stainless steel. And that is only produced right now by a company in Japan. That's the only producer of that material in quantity.
So the secret sauce there is the layering and the manufacturing techniques involved, but I didn't hear any mention of like rare earth metals or anything like that.
Well, there's barium, copper oxide with lanthanum or one of the other rare earths that basically makes those high temperature superconductors, and that's an area that's a work in progress. People are trying, to extend the temperature range of these materials and stuff like that. So that's going to be competitive, I think, very quickly. And I think this company in Japan that it's called Faraday, incidentally, which is interesting. They have cornered the market right now, and Commonwealth Fusion is buying enormous amounts of this tape to wind those coils, those magnets. But there will be other people making that stuff. I mean, it's I'm sure what they're making in Japan is patented, but you can't hide the fundamentals from the industry, I think. As the demand for those kind of magnets increases, because they're going to go into MRI machines and things like that, that they're so much better to use than the high temperature superconductor, the low temperature superconductors.
It's one thing that you have to remember, Ted, at least my understanding, is although we call them rare earths, the quantities available are fairly large. The difficulty is, in fact, refining the ore into the constituent materials. And so, we call them rare earths. I don't know why they got called rare earths, but they're physically abundant.
Yes. Yeah. No. They are, and a lot of them came out of explorational geology, geophysics in Sweden. There's actually a one little town in Sweden that has 4 elements in the periodic table named after it: yttrium, ytterbium, terbium. What's the 4th one?
The rubidium?
Yeah. So,
Very impressive.
Yeah.
There are only so many elements.
Carl, what do you got?
Yes. So first of all, unfortunately, even though they may be abundant, we have somehow let China control most of the processing. And so that's an important choke point at the moment.
Yeah, I think that's a temporary choke point. That's it's a matter of the people who want to do the processing have faced very stringent environmental regulations that have priced them off the marketplace right now. But as the materials will be extracted here, right now, most of the materials are being extracted in places like Africa, various third world type settings. But we're going to start producing those materials, and then the question is, can we refine them without having uneconomic means of defining the criteria for production? And I think that'll happen. People will realize the value of it is. As I said, the quantities are not huge. It's just
there's a company in Woburn that is now taking mine material coming from mines, yeah. And they're they say, and they're in the process of building up here, extracting the rare earths from that right now. And they're saying, at least publicly, that they can get vast quantities just from the mine tailings.
Yeah.
So they're actually doing it now within the U.S.
Yeah, that's another one of the companies. Spark, Commonwealth Fusion, and Spark came out of MIT through this MIT sort of startup incubator thing called the Engine. Yeah. And this that company in Woburn is another engine company.